Hello YouTube, RJ. Well, today we're going to talk about a component that gets very little time spent on it. It doesn't seem to get a lot of love, but probably should, and that's the Triac. Now, a Triac is a type of thyristor. You can kind of think of a Triac as a transistor for AC, where we know that normal transistors are DC devices and will only conduct current in one direction. A Triac can conduct current in both directions. Now, it has a few little weird characteristics, so we'll get into that. Okay, so here's the symbol for a triac. We're going to talk about a triac today, and we're going to talk about what it is, what you use them for, why they are the master of AC. At the end, we're going to go over why they're the Christmas hero. And so let's take a look at the schematic here, and what you'll see is you've got a gate, just like many transistors, but you've got some terminals. You don't have collectors and emitters. You've got T1 and T2. These are neither collectors or emitters per se because we're dealing with AC. Current can be flowing either direction through this device. Now, triacs operate very different than most semiconductor devices as far as transistors and such. You can't think of them as a MOSFET. A MOSFET, when you put voltage to the gate, turns on and lets current one direction through the transistor. With a triac, when you put voltage to a gate, it turns on, but with a MOSFET turning the gate voltage off would stop your flow. That won't necessarily happen. Turning the voltage off the gate does not make the triac stop conducting. So when I say that, what I mean is at least not immediately. You don't have complete control of when this turns off. You only have control of when it turns on. So let me explain that part of it. So here we're looking at an AC waveform. Let me bring that out a little bit. And what you see here is at 0 degrees of, this is your phase, the angle of conduction, if you will. At 0, your voltage is actually 0. There is no voltage, so there is no current being conducted. And you get a sine oil shaped wave, as you're used to seeing in AC power. It comes up, and our typical in America are what we consider 120 volts here, 117, 120, depending on who you ask. We hit about 170 volts at the peak. It's RMS, or average voltage, if you will, that's 120 volts. So we actually go above 120 and come down, but the average is 120 because so much of the time here and here is below 170. If this was a square wave where we went straight to 170, ran and come straight down, it would be 170, but we're losing energy here on these downslopes as the voltage gets less and less and less and less. So we average 120, or at least average is probably not the correct term, but we'll say that it's root mean square. Basically, how much energy is under this curve in here. We start with nothing. We, at one point for a short time, hit 170 and we come back to 0. Now we come back to 0 in the United States where it's 60 hertz. You have to calibrate this a little for 50 hertz. But for 60 hertz, every 8.333 millisecond, actually this runs on forever, but 8.333 milliseconds, we do what's called a zero cross. That's what we call the point where the waveform goes through the point where it is 0 volts. There is no power available. Then we begin what we call the negative side of the sign. We head down doing the same thing, repeating the same thing with the opposite current flow. And we end that at the 360 degree point at 16.666 milliseconds. Now, if you multiply this by 60 times, you'll get 1,000 milliseconds, which is 1 second. So 60 times a second, we see this waveform. Now, why does this matter? Well, because of the way a triac works. Triacs only turn on when they get a voltage to their gate. But once a triac gets turned on, it will keep conducting voltage as long as there's voltage there. You have to get down to some certain very low point before the triac will turn off. So you can turn it on. You don't have to keep a voltage continuously on the gate. A literal pulse will turn it on. It'll stay on all by itself. Now, you don't hurt it by applying a gate voltage and leaving it there, but you don't have to leave the gate voltage there. So if I was to not apply voltage to the gate, and we began a cycle, the Triac would be off. There'd be no voltage. We'd just run along this line here. Let's say I waited till this point right here and I sent a pulse to the Triac. Our voltage would spike straight up to this point and then slope down till here and then stop. If I did a pulse, it would stop. There'd be no voltage on the gate at this point. It would turn off because it is not conducting any current, and it would be off again. We would start off across here. That means that we can only control the turn on. If we turn one on, we have to wait till we get to a zero cross before it will turn off on its own. We have no control of that. So that's an important point to understand to go into the next thing we're going to do. Okay, so this leads into one of the questions. What do we do with Triacs? Well, for one thing, we use them as switches. They're wonderful AC switches. We can turn on AC voltage as we want. We can turn it off, although there can be as much as 8.33 milliseconds after we tell it to turn off before the power turns off. But in most cases, that doesn't matter. You know, a human doesn't even notice that. So basically, we could use it to turn on the power at any point. So if you had a light bulb that you wanted to turn on and turn off from a low voltage controller, like say a Arduino or some kind of microcontroller or some device, a Triac would be a wonderful device to do it with. Basically, you would apply a voltage to the gate and hold it on as long as you want the light to be on. That would turn the voltage on immediately, as in our previous diagram, run all the way through, and where it would normally turn off, there's a voltage on the gate, so it would keep conducting, and you'd get your full wave, and your light would be on. When you wanted it off, you would turn the voltage off to the gate, and at the very next zero cross, it would stop conducting and your light would go out. It's basically a switch, a relay. Think of it as a relay, but it's a relay for AC. And that's what it's used. All these little solid state relays you see that you can buy online, that's how they work. There's some extra components we'll talk about in them, but this diagram's here for a reason. Let's say that we were not applying a voltage to our Triac, and our cycle was going on and we had no voltage, and all of a sudden, halfway through at 4.166 milliseconds through of this cycle, half cycle, we sent a voltage to the Triac. It would turn on straight up to the voltage it's at currently, this is where we are in the cycle, and it would follow the rest of the cycle out until zero cross. Now, if we only did a pulse, when we got here, it would turn off on its own, and if we waited another 4.166 milliseconds after that point, we could turn it on, go straight up to the peak, and follow the next waveform all the way down. Now, what would this do for us? Notice that we have a lot less area under this waveform, and so our average voltage would, I'm just using 60 here to give you an idea since 120 was full. Let's say 60 volts. We would have 60 volts average. So what would we use something like this for? Well, how about a dimmer? How about the dimmers that you slide up and down on the wall to control the lights in your house? Often they're nothing but a Triac with a device that actually does this for you. Now, you could put a big rheostat in the wall that would drop the voltage resistively to turn the lights down. But what would be wrong with that? Well, the amount of power wasted turned into heat would be ridiculous. So that's a very inefficient way of doing it. On the other hand, this is a very efficient way to do it because we just leave the power turned off until we're halfway through. If we're dimming halfway, bounce it on, let it run through. We're not generating a bunch of heat. The power is all going into your lighting fixture. It's just less power, not necessarily less voltage, not necessarily less current, just half of the cycle. So the area under here is half the power. So the light dims. This is how we create light controllers for everything. We dim lights doing this. We can come along here and turn it on here, maybe right here, and get, say, a fifth of the power or a tenth of the power, or we can increase this up to where we turn it on very quickly after the cycle starts and we get most of our current, or our power, but not all of it. So we just dim the light just a little bit. So these are very handy circuits. And this zero cross becomes very important because to do this, the device that you're controlling this with needs to know where we are in a cycle. And the way they do that is by using a zero cross circuit that actually watches for this point informs your controller that, hey, I'm at 0, and allows it to start a timer and decide where it wants to turn on the power based on that. It always knows where this is at. And if I was doing this, for example, if this is supposed to be 50%, basically when my 0 cross circuitry pulsed my CPU and said, okay, you're 0 cross, I would start counting, and I would count 4.166 milliseconds, and then I would send the pulse to my Triac to turn my power on, and that's how I would get half my power. So let's move along. Okay, so let's take a look at a schematic of how this would work. This is basically a solid state relay. This is our Triac right here. We've got AC coming in with one leg fed into one side of the Triac, the other leg fed into our load. Coming out of our Triac, our load, which is a lamp, is connected to this other side of the Triac. And then the gate runs in, and we put a resistor in here. We run it through. This is a Triac opticoupler. They're special opticouplers designed for Triacs, and we'll look at some data sheets on these in a moment. But what happens is it does not conduct. It's based on photo-optical isolation. It does not conduct unless the light is shining on it. If light shining on it, then this power comes through into the gate, turns on your Triac. This LED inside of the optocoupler is fed from, in this case, it's going to be a CPU that's going to turn it on and off. You'd have a resistor in here, typically, to control your current, but it would come through the LED to ground. So basically, you're just it's like hooking an LED up. If you were using like Arduino, it's no different than having an LED on an Arduino and controlling it. But when you control the LED, you're actually controlling the turn on of a Triac. So this is the circuit and how it works. Soon as you turn on the LED here, it sends a voltage to the Triac, isolated, many thousands of volts typically, so that all your low voltage stuff is safe and protected from the high voltages. Feeds it in to turn on the Triac. Current now flows through the circuit and the light turns on. Turn off this LED. This stops conducting. Comes over, no voltage goes to the Triac, so we have to wait for the 0 cross, but when the 0 cross hits, this will automatically then turn off. So I've just described a solid state relay into a light dimmer. Okay, so now what we're going to do is we're going to go look at some data sheets, and then we'll jump over and we'll look at some real world operation of these. Okay, here's a BTA06 series Triac, 6 amp Triac. Very familiar with this part. It's rated for 6 amp of current, anywhere from 600 to 800 volts. The gate requires 5 to 50 milliamps to turn on. Okay, so here's a data sheet on the optocoupler. I've used a lot of these. The MOC 3020, isolation of up to 5 kilovolts. It's a 6-pin dip photocoupler, Triac driver output. It's got a high repetitive peak off-state voltage of a minimum of 400 volts. Used for motor control, solid state relays, triggering high power thyristors, and Triac's household use equipment. Here's what it looks like. Here's your LED. Here is your inborn Triac. It's actually a photo Triac, if you will. And that's really, what we need to know. Okay, now I'm going to show you just what we can do with this equipment.
Born on Christmas Day to save us all time. Angels we've heard on high.
I'd love to show you my whole Christmas light show, but that I'd get copyright struck on the music. Okay, on the bench we have a Lynx Express, one of the light controllers that I created many years ago, along with a whole lot of other controllers for Christmas lights in my day of doing that for many years. And let's open up and see what we got here. So here is a Lynx controller. We can see here all of the Triacs, 16 Triacs, 16-channel controller. And on this side you can see the PIC microcontroller, the LED displays, the 2 push buttons that did all of the programming. This is a LED driver. These are optocouplers, one that we looked at, one for each channel. Each one of these optocouplers drive one of the Triacs through this resistor. Each channel has an optocoupler, a resistor, and a paired LED. We have enough drive out of this chip not only to drive the optocoupler, but even enough to drive an LED for indication. You got a place up here to plug in a wireless module. If you go online and search Link Express light controller, you get lots of web or YouTube videos of people using these, doing light shows, playing around with wireless. Little module plugged in here lets you run it without having to run data cables all over the yard. Pretty straightforward setup. And then all of your AC came in 2 cables. You had 2 cables to feed. You could do them as a single or dual feed. And if you did a single feed, you were limited, had a current limit. If you went dual feeds, you could increase your current limit. There was a test that we'll see here, a test procedure that would run through some tests for you. So anyway, what I've done here is I've taken channel 8 output, plugged into our dim bulb tester to give us something we can see, and doing something you don't want to do, which is jump across a outlet. But in this case, it's a controlled situation. I know what I feel safe. It's insulated wire. I don't have bare wire out here, so it's turned on. So let's plug this in. Let's see if this rascal will work after all these years. I haven't used these in probably 10 years or more. So we get 5 volts and 3.3, and we have a boot up going. Links Express, 60 hertz, channel 1. 60 hertz because these were designed to run 60 hertz, or if you program it, you can tell it to run 50 hertz. So you can use it on 50 hertz systems. Channel 1 means that DMX channel 1 is the first channel of this controller. So channel 1 through 16 DMX, and then if you had your next controller, you would program to 17, it would be 17 the next 16, and so that's how you adjusted these. You could have multiple of these on the same channels, by the way, if you were mirroring things. So we're up and running, so we can go, let's go to test. Let's run the test. You'll see the LEDs will do a test, then we're going to start going through the channels. When we hit 8, the light should come on. Look at that. It did. And as it blinks the channels, the light should blink. And then when it ends, it leaves you with LED 2 is your zero cross, meaning the zero cross circuitry that we talked about earlier. It's working. It's recognizing a zero cross. LED 4 tells me done. The test is completed all the way through the test successfully. The only thing we don't have is LED 3 is your DMX. If there's DMX being recognized by this controller, that light will light. I don't have any DMX going in, so obviously it doesn't. That's basically it. That's a Lynx Express controller. Big heat sink, get rid of heat so that we can handle quite a bit of power. So that's a Lynx light controller. And that's how the Triac is the Christmas hero, because it allowed us to do so many inexpensive controllers, to do big Christmas shows and put smiles on so many kids, old and young. If it wasn't for the ability for the Triac to handle AC and control it so well, so cheaply, there's just no way we could have done that. That ends this video. I hope you learned something. I hope I entertained you. I hope you'll click the subscribe button, the like button, and the notify button would be fantastic. So thanks a lot. See you in the next video.